Okay, so now we're actually already going to start the next part, which is chapter 3. Now, chapter 3 deals with radiative transfer, or as it is called, radiative transfer versus radiation in equilibrium. And hopefully we will see what I mean with that. Now, remember when we introduced the specific intensity, we said it was along some beam traveling in some direction n hat, okay? And then we said that the specific intensity is constant along this ray as long as there is no interaction with matter. Okay, but what if there is? And that's, you know, the case of analyzing radiative transfer deals with that. So how can we then set this up? Okay, then we're going to have some specific intensity going into some parts of this beam, okay? So we're going to cut out a little part here. And in this part now, along some delta S, where delta S now is a segment along this ray, okay? The radiation and matter can interact. And then we're interested in, okay, this is what goes in. How does this change? What is coming out? So then we will have that delta I nu, that is the change in the specific intensity, is just this one, okay? That depends on now the three different processes that we already said could happen. Remember, we had the emission of material, we had the absorption, and we also had scattering. Okay? So first we're going to analyze, okay, what energy is added to the beam? And then we're going to describe this with a coefficient. We're going to call it eta at a specific frequency nu. So that's going to describe how much energy, or specific intensity in this case, is added to the beam in this segment. And intuitively then, yeah, this is going to be proportional also to the length of the segment. Okay? We're not going to specify what this is now or where it comes from. Now, we can also then absorb material, as we discussed. Now, absorption, that's when you have radiation and then it's absorbed by the matter, for example, in a line transition or something like that, that we briefly mentioned last week. Okay? So then energy is removed, and that we're going to describe by another coefficient. We're going to call it alpha nu. Now, that alpha nu then will also be proportional to the length segment, intuitively, but it's actually also proportional to the intensity that is coming in at that point, which hopefully is also intuitive, because if you don't have any intensity coming in, of course, you can't absorb anything. There's nothing there. So that's going to be proportional to I nu at that point. Okay? So this will be our emission coefficient, and this will be our extinction or absorption coefficient. Extinction coefficient then normally deals with both absorption and scattering. That's, yeah, the difference. So the topic for calculating these, yeah, that is actually then in the coming chapters. Then we will see how different radiative processes that can be important in various astrophysical situations can give rise to various different expressions for these emission coefficients and these extinction coefficients. Now, in this chapter, we will always take them for, okay, we're going to say that we know what they are, and then we're going to analyze the nature of the transfer of radiation here in such situations where we know these. Okay? So first, we can just identify this. We can rewrite it to say that delta I nu divided by delta S is either nu minus a nu I nu. And if we put this now on differential form, which I did very mathematically tactically like this, okay? Then we have the basic equation of radiative transfer. Okay? So, importantly, along a ray in the n-hat direction. We're going to come to situations later where we're going to put this in some sort of geometric coordinate systems as well, right? Now, first thing first, we're going to look into this, and then we're going to say, okay, well, remember what we said already in the first and in the outset, in the absence of interactions with matter, the specific intensity should be constant, right? So that's the first thing we need to check. So indeed, in that case, eta nu equals alpha nu is going to be 0. There is no interactions, right? And that just gives directly the I nu ds equals to 0, or I nu equals to constant. So we check that box. Good. Now we're going to see the other situation today. We're going to start with that, actually. And that is the case of equilibrium radiation. Okay? Now, such equilibrium radiation, in that case, we can use what is known as Kirchhoff's law, which actually states that the emission has to be balanced by the absorption coefficient times the specific intensity. Okay? That's Kirchhoff's law. Now you just plug this in here, and you see again that in such a situation, again, the I nu ds equals to 0, or I nu is constant. So in both limits, so to say, we get that the specific intensity is constant. Now, in this case, this is equilibrium radiation, and then the radiation field, specific intensity, is described by a very famous spectral shape function. The spectral shape that the specific intensity in that case has is given by 2h nu cube c squared 1 over e to the minus h nu divided by kt minus I, which we then define as b nu, which is only a function of t. This is the Planck function, or Planck's law of radiation. As you can see, it is a very strong function of frequency. Yeah? It depends on temperature, not on density, on the material density, right? And ideally, in order for this to be fulfilled, the temperature actually has to be equal everywhere. Sometimes when we deal with radiative transfer, we'll come to this later during the course, we can assume that this holds locally. For example, in plane parallel layers in an atmosphere around a star or in an accretion disk or something like that. Then this might hold locally, but not globally. Okay? And we will come to such local thermodynamic equilibrium situations later on. We will also look at, in the transition between chapter 4 and 5, at the origin of Planck's law of derivation, actually even repeating his original derivation of it, and see how it actually arose, which has a quite interesting history to it, because as you may know, this is where he first came up with it as basically a mathematical trick, a way to match what he found empirically, and then he came up with his quantum oscillator hypothesis in order to explain that, which essentially was the dawn of quantum mechanics, right? But for that we need a little bit more knowledge, so we'll do that later during the course. For now, we will take Planck's radiation law for given, and we know it, and we will discuss and analyze its properties. Okay? So, now, first thing you can notice is the spectral shape. So if we, for example, now just do a very schematic plot where we plot something like the logarithm of a frequency, and then we have B nu for a given temperature here, there, at the low frequency limit, we will essentially have a power law behavior, and then we will have a peak and an exponential cutoff. So in this regime, we have a power law, we have some sort of peak value, and then we have an exponential cutoff. Okay. So let's see if we can understand this. Well, the power law dependence, we can use this, okay? And then we can make the assumption that, okay, low frequencies, h nu divided by kt, if that is much, much smaller than 1. So, and this is actually very important, where you reach this regime depends highly on the temperature. So if we analyze the cosmic background radiation today, which is very cool, on the order of 3 Kelvin, then we have to go to much, much lower frequencies or higher wavelengths in order to apply this limit than if we analyze the spectra from a hot star, which is perhaps 40,000 Kelvin on the surface. The important thing for this power law regime to hold is this, okay? Now, in this regime, we can apply a Taylor expansion, and if it's one Taylor expansion that you need to know in this course, it's this, that e to the x is approximately 1 plus x if 0 is smaller than x, and it's much, much smaller than 1. Okay? This will come back both here and then in the radiative transfer equation, etc. So that's a Taylor expansion. So we apply this there, because that's essentially what we have there, right? So then we can say that B nu in the so-called Rayleigh-Jeans limit for given and t, that's 2h nu cubed divided by c squared, 1 over, and then I use this, so then it's 1 plus h nu divided by k2 minus 1. So this is interesting. We see a number of interesting features here. We get 2k minus c squared. Note how h is canceling. Then we get nu squared t. So in this Rayleigh-Jeans regime, we have one that for a given temperature, B nu is proportional to nu squared. We also have that it is directly proportional to the temperature, yeah? And we have gotten rid of Planck's constant, which is h, as we know. And this is indeed the classical limit. And we will see either at the end of today or next week how it also leads to what we call the ultraviolet catastrophe and what that actually was. Okay? You see the power law dependence there, right? Now, in the opposite regime, you have h nu divided by kt much, much smaller than 1. Did I really? Yeah, sometimes. Now, in this, that is called then the Wien limit, okay? And then you can see that you're going to be proportional then to mu cubed e to the minus h nu kt. And as you know, if you're up against an exponential, you're always going to lose, which is indeed why you get this drastic exponential cutoff. The power law doesn't stand a chance. Yeah, that's a basic thing from calculus. Did I do something? Yes. Thank you. I was pointed out from the audience that both here I had h nu over kt much, much smaller than 1, and then I repeated it here. Hopefully I said it wrong. It should, of course, be much, much greater than 1 if I said it wrong as well. My apologies. Because if it's much, much greater than 1, you can see that you can neglect the minus 1 there, and that's the whole purpose. And that's how you can write it like this, okay? And that's how the exponential eventually will win out. The higher and higher frequency we go to, and we will get the exponential cutoff. Yeah? And that's indeed what was required in order to avoid the ultraviolet catastrophe, by the way. The third thing we said was, okay, can we do something useful with the peak? Well, actually, in astronomy, the peak turns out to be very, very useful. So we're going to look at that a little bit. But it's mostly intuitive and for further calculations also to do that in wavelength space rather than in frequency space. So then we have to take a little bit of a detour there to say that, and this is important, remember that when we introduce this specific intensity, you have to always think about that technically it's only defined in a small waveband interval, okay? Such that the preserved quantity is really b nu t, the nu is b lambda t, the lambda. That was the same for the specific intensity. So in order to get the wavelength version of the Planck function from the frequency-dependent version, we can't just plug in the wavelength there and then just have it. We have to also take into account the difference in the nu, right? So technically, one should always write that the real quantity that one analyzes is this one, right? So in this case, you can see that b lambda of t is just b nu of t, and then it's just the nu, the lambda, where of course we know that c equals to nu lambda. Now, your first little homework will of course then be to verify the version that you find in the book for b lambda of t. The second one is to, okay, we want the peak. How do we take the peak? Well, we just set the derivative for a given temperature. It's a function of lambda now to 0. And then we solve it. Okay? Now, the interesting thing from an astronomical standpoint is here that when you do this, and that is also an exercise to solve this integral and verify that indeed what you find is that the peak wavelength, lambda max, times the temperature of the black body radiator is always a constant. Okay? Lambda max now being the wavelength at which this is maximum, that is where the derivative is 0. Now, silly enough, I am not sure that I brought with me the constant, so I'm going to ask one of you to look it up in the lecture notes in some convenient units here. Can somebody do that? Or me now? Normally we have it in some inverse Ångström and Kelvin. Sorry? 2897.8. And what are the units then? Micrometer Kelvin, or was it millimeter? No. Micrometer Kelvin. Okay, nice. So, there we can see here, right? So, let's now assume that we observe something, say a stellar spectra. And that stellar spectra is not exactly a black body, as we know, but it's roughly a black body in wavelength space, so perhaps it's something like this. And then we observe that this peak wavelength here in that stellar spectra is, okay, it's at 500 nanometers, right? Now, what temperature is that? Okay, so then we have to see that the temperature then is 2897.8 times micrometer Kelvin. So we have to do this to micrometer. What is that? 0.5 micrometer, right? 0.5 micrometer. So this is going to be on the order of 5,700 Kelvin. Well, this is 900, so 5,800 Kelvin. Okay? Can we tell an object that might have a surface temperature roughly 5,800 Kelvin? The sun. And where's the peak wavelength of the sun, the emitted spectrum? Green, which is around 500 nanometers. This is an approximate, but you can tell that immediately by just looking at the spectra from any object, and in the lecture notes, in the course book, we have a few stars. You can just get the first guess of its temperature by just applying this. So for example, if a star is much hotter than the sun on surface, say 4 times hotter, yeah, then the peak wavelength will be roughly at 4 times lower wavelengths. So instead of at 500 nanometers, yeah, it's going to be at around 100 and 150 nanometers. Now, why is this important? Well, then we have actually gone to a different waveband. Then we're in the ultraviolet. And the ultraviolet, for example, we can't observe from here on Earth. This we have discussed, because it gets absorbed. So then we needed to shut up these telescopes into orbits above the Earth's atmosphere in order to observe various astrophysical objects in the ultraviolet. Okay? That was the James Webb telescope. Okay? Similarly, if you have a cooler object, yeah, then the peak wavelengths will be further to the higher wavelengths. So for example, if you now are interested in something like planets around other stars, so-called exoplanets, yeah, then you might be interested in wavelengths that are much, much higher, because the temperatures might be much lower. So perhaps you want to go to the infrared and observe those. That's where, for example, the James Webb telescope, the new one, is tuned to be very efficient. You can even apply this to galaxies. For example, you can look at the spectra from a whole galaxy, which then contains of billions and billions of stars, and then you can see, well, you know, this galaxy spectra from an elliptical galaxies has its peak in the wavelength very much to the red. Well, what does this mean? Well, no, to the red. Well, to the against the infrared. Yeah? Well, it means that the objects that are emitting, that is dominating this source, they have cooler temperatures. And typically such elliptical galaxies are also called red and dead galaxies. They have no active star formation, so the young, very massive stars that shine a lot in the blue, they have died out long since, and what is left are these red dwarf stars, such as our sun, and even more so, even lower mass, cooler stars. And then you see this directly reflected in the spectra from the whole galaxy, because the peak wavelengths are shifted to the red. And then you compare this to like a spiral galaxy with a lot of active star formation, or even a so-called starburst galaxy. There, the peak wavelengths, they will be shifted much, much to the blue. And that's because there are so much active star formation going on, such that there is a lot of these young, very massive, hot stars which are shining and dominating then the total light. So you will get much, much the light. And there's also some such galaxy spectra for you in the course book that you can notify. But realize that only by looking at this, we can already get a feeling for now the temperature of various astrophysical objects that come to us. And then and I will just leave you with that, what we will do next. Next week we will finalize by looking at also the integrated properties of the Planck curve. Because what you should have already realized is that, okay, in the Planck curve, there is no density dependence, right? But there's also no angle dependence. So if we now plug in this, for example, in our energy density, right? Our energy density, remember, is defined as this, and then nu, 0 to infinity, and then we have I nu, right? So now we replace that with B nu of T divided by C, and then the nu, the omega. But there is already no angle dependence in the Planck function. The Planck function is, as it should be, because it's equilibrium radiation, isotropic. And this is where this comes back. So this we can already take out. It's going to bring 4 pi, and we just have to frequency integrate the Planck function. And then we will see what comes out. And indeed, When you do this now, for the full, you will get an expression. However, when you do this now in the classical Rayleigh-Jeans black body, yeah, and you integrate this now, so it's 4 pi, and then nu 0 to infinity, and then b nu Rayleigh-Jeans of t divided by c, the nu, you will see that this indeed goes to infinity. And we will verify this, of course, and you can already do that if you wish, because you can just look at the expression and realize this, and this indeed was then what was called the ultraviolet catastrophe of classical physics. So already there, people knew very much that something is wrong here, because we predict that the radiation energy density from any given black body, whether it be me or a star, I'm a black body roughly emitting around 300 Kelvin, right? That's why we emit in the infrared by the same law as before. I should have a total energy density that is infinite. Well, that's not really the case. But more on that later, and we will continue to next week analyze more on black body radiation and then also go to the transport of radiation. Thanks for today.